Hi there. We are doing section 1.9 on hybridized atomic orbitals. We touched on it a little bit at 1.6 because I got a little excited, but hopefully you'll read 1.9 and you'll see that I jumped the gun a little bit. However, I would like to share with you in my own words a little bit more about hybridization because we can cover sp3, sp2, and sp hybridization together, and then hopefully the book will round out exactly what you need to know. So let's have a look here where we left off in 1.6, talking about atomic orbitals. And if you remember, we were looking at a tetrahedral carbon. In this case, they were just bonded to four hydrogens. And that tetrahedral carbon, we said, could not have the electron configuration shown here. And that's because the electron configuration drawn only has two available spots for bonding. And yet we want to look at a tetrahedral carbon that has four. So what does the universe do with this? Well, the universe instead will hybridize the top four orbitals. I promise I know that my handwriting is bad and I'm sorry. I will try to write as well as possible. Okay. So they're going to, the universe hybridizes the 2p and the 2s orbitals. And by that, I mean those orbitals are mixed together to make this electron configuration, where the energy is going up. So we still have our 1s orbital filled with electrons, but now we have four degenerate sp3 orbitals. Degenerate meaning the same energy level. And each of these has one electron, just like we would hope if we need to make four bonds. Okay, now, what do you get? Let's see. We take one spherical s orbital, and we take three p orbitals, where each of them have different lobe colors depending on if they are positive or negative. So you mix those three together, and you can imagine that you'll only have around 25% S character and 75% P character because you're mixing three P's and one S. And when you do that, what you get is a really funny looking orbital with a whole lot on one side and not much on the other. I actually want to use this color just to be consistent. And this is an sp3 orbital. Now, one other slightly interesting thing, I find it interesting because I'm a chemistry professor, is that these sp3 orbitals are actually the reason why you have tetrahedral geometry, because as the carbon makes its bonding with the hydrogen, those electron clouds are so big they have to stretch out as far as possible away from each other. And the the angle between the two is actually 109.5, which is the tetrahedral angle of bonding there. All right, so that's for sp3. But what about for sp2? Because if you look at an atom or a molecule, sorry, like this carbocation, where the carbon is bound to three hydrogens and the carbon then also has a positive charge on it, it's called a carbocation because cations are the same word for positive charges in chemistry, if you remember, and it's on a carbon, so we cleverly call it a carbocation. So here, its energy level diagram looks a little funnier because we have the 1s orbital and the 2s orbital that also has electrons like normal. But the 2p only has one electron instead of two. And the other weird thing is that we can't make a tetrahedral geometry like above for the sp3 version because we don't have enough electrons. So how do we rectify this? How do we address this problem? So what we do, or what nature does, is it hybridizes. Something is going on with my pen, I'm sorry. It hybridizes. Yeah, I don't like this. Hold on, I'm going to try and fix it. Okay, as I said, this hybridizes to give us instead energy is always increasing, going up. What we do is now we have our 1s, oh, I drew in the wrong place, sorry. Our 1s as always, but now we have 2 sp2 orbitals, and we only have 3 of them to go with our 3 electrons. So those 3 electrons each get placed in these 3 orbitals, but we have 1 left. Remember? Because we only took 3 to be hybridized, and we have left 1p orbital. So the 2p is actually still present. It just doesn't have any electrons there. So using this, we can say that the carbon is using a 2p orbital, and those 2p orbitals are now mixed of 1s that's spherical and 2p's that have 2 lobes as before. So these orbitals are going to have much more s character, and they're going to have much less of a very funny shape than we saw before. And they're going to look like this. So this is sp2, and it's going to have, whoops, a shape that looks a little more reasonable there. So this carbon is going to use these sp2 orbitals to bond to the hydrogens, and the positive charge there is going to exist in a p orbital because it doesn't have any electrons present. Okay, so last, what about another situation where we are instead, this is very hypothetical now, we are instead going to hybridize only 2 instead of 3. So what if we have, let's say, I don't think I like that example. Okay, I'm back. So what if now, instead of hybridizing 2 or 3 orbitals, we come into a situation where we're going to hybridize even fewer? Okay, so imagine that we are dealing with this molecule. You might have heard of this molecule before. This is hydrogen cyanide. And see here, this is, I drew what's called a triple bond. And in hydrogen cyanide, now it's only actually bound with a sigma type bond to 2 molecules. So it only really needs to use or hybridize two orbitals. So if we again draw our energy level diagram where E is increasing, we have the 1s as always, and it's filled with electrons. Wow, really some lagging happening. But we also have the 2s as always. Why? Why are you doing this? The 2s. Sorry, I'm trying. Technology does not like me today. There we go, 2s. It again has 2 electrons. But we also have, again, the 2p. Sorry, we're almost there. 2p, and normally the carbon will again have the 2 electrons, but we only need electrons, or we only need to hybridize 2 orbitals. So, like I said, because it's only bonding to 2 atoms, so let's hybridize these 2. Because we only need 2 orbitals, and we only need 2 electrons, as before. So that's what nature does. Oh, look, it's working so much better now. So if we make the new energy level diagram, we have 1s that has 2 there, but then also the 2 sp orbitals with doubly degenerate states, which are lower in energy than the 2p orbitals that also have 2 electrons. So now what this looks like is that we are mixing 1s and 1p to make our sp orbital. And so now, since we're mixing 50-50 s and p, it's going to have the properties of both and be very funny looking and very small, because it will be very close to the nucleus of the carbon. So that means the carbon will bond to both the nitrogen and the hydrogen with these funny looking small small sp orbitals, while the hydrogen has a normal one and the nitrogen also has a funny little sp orbital. We can get to that at another time. But if you remember, we still have these 2 p orbitals up here that we have to account for. So the carbon is going to have 1 p orbital above, and I'm going to try and draw this, 1 p orbital kind of jutting out to the side over here. And that's how they make a triple bond with the nitrogen here, because the nitrogen also has a triple bond to match the carbon. And there is overlap between the two. The same thing happens in a double bond, but a double bond has 1 p orbital instead of 2. Okay, so I hope you found this helpful in hybridization. We'll definitely be covering hybridization more in this course, but this is a good little review about hybridization from general chemistry. I hope you found this interesting and helpful. This is section 1.9.